So I wanted to finish up on Michaelis-Menten kinetics. There's just a couple of things left to do. Recall that we derived this expression for the appearance of product based on the steady state approximation, and the mechanism that's associated with this equation is binding of the substrate by the catalyst to get an enzyme substrate complex, rate determining conversion of substrate to product within that complex, and then afterwards fast dissociation of product from the complex. And if you make the steady state approximation based on the enzyme substrate complex, you get this equation. K-cat we've talked about, and I was actually wrong last time on the units. You've got two concentration elements in the numerator, so this would be molar squared. These are both in concentration units in the denominator. So you'd have a molar unit up here. Your rate needs to be in molar per second. So actually, the units of K-cat are just per molar. I'm sorry, forgive me, are just 1/seconds, hertz or per seconds. So we call K-cat the turnover number. And this is basically how many times a second the enzyme converts substrate into product. Km, the Michaelis constant, is complicated. It has, and I guess it might be good to, I'm going to go to last time's lecture and just copy down the equation. That's the setup for the Michaelis-Menten kinetics so that you can see what the rate constants are. Sorry about that. Paste that in there. Oops, shrink. Close enough. So the Michaelis constant is the sum of the reverse rate, enzyme substrate dissociation, and then the rate of catalysis, K-cat. And I'm sorry, both of these are in per seconds. And then K1 is in per molar per second. And so overall, the Michaelis constant is in units of molar. And we talked about how last time equilibrium constants in units of molar make you think of binding constants. And interpreting the Michaelis constant can be difficult. If the rate of going back enzyme product dissociation is very much faster than the rate of converting substrate into product, then the Michaelis constant resembles the binding constant between enzyme and substrate. So looking at this equation, if we just took this part, binding of enzyme and substrate to get the complex, the equilibrium constant for that reaction, the association constant, would be K1 over K minus 1. The dissociation constant, or Kd, would equal K minus 1 over K1. So when K minus 1 is much greater than Km, you can think of it as the binding constant. But this is only the case for really cruddy enzymes because, of course, you want Kcat to be high. So for the best enzymes where Kcat is much higher than the K minus 1, the Michaelis constant becomes something that's hard to interpret, but whatever it means, it doesn't mean Kd. So you have to be a little bit careful when interpreting the Michaelis constant. A couple of other things to get out of Michaelis-Menten kinetics is that by comparing the concentration of substrate you have versus the concentration versus the Michaelis constant, you can predict changes in the reaction mechanism. So, or changes in the speed of the reaction, rather. Sorry. So if the substrate concentration is much, much greater than Km, then your rate no longer depends on substrate concentration, because that substrate concentration now gets factored out, and the rate is only determined by the turnover number, kcat, and your starting enzyme concentration. And both of those are constants, so this represents sort of saturation of the enzyme with the substrate. You can't go any faster because all of your enzyme is bound, and the rate is only determined by how much enzyme you have and what the speed of kcat is, and adding more substrate doesn't get you anything. So if we were to plot the rate of the reaction dp dt versus substrate concentration, there would be some value km, and if substrate concentration is higher than km, we start to plateau. Okay? And this is the typical saturation curve that you get with enzyme kinetics. In contrast, if substrate concentration is very, very low, much lower than Km, then dP dt is just kcat times enzyme concentration times substrate concentration divided by Km. And you can think of this as a pseudo second order rate constant, K obs times enzyme concentration times substrate concentration, where K obs is equal to kcat over Km. And it turns out that kcat over Km is something that people call the specificity constant. And it's a useful way to compare enzyme activity when you change different substrates, because of course you've got two things to deal with there. When you change substrates, the reaction might be slower because the enzyme doesn't bind the substrate quite as well, or because the substrate isn't catalyzed. The conversion of that new substrate to the new product is slower. So you've got both the turnover and the enzyme binding to deal with when you change the substrate of an enzyme, and you can get both of those things in your comparison by looking at these kcat over Km values. Let's see. From an evolutionary perspective, whether your substrate concentration is greater than your Michaelis constant or less than your Michaelis constant influences what kind of pressure evolution might put on your enzyme in order to improve catalysis. So your text makes this point, and if you have any questions, feel free to interrupt me. You don't have to raise your hand. You can, I don't have the chat function in front of me, but just speak up if you have questions and stop me. Your text points out a couple of different scenarios where an enzyme might not be optimized for its particular conditions. For example, what if the physiological concentration of your substrate is much greater than the Michaelis constant? So I'm going to plot here a reaction coordinate diagram with energy on this axis and reaction coordinate on this axis. If the substrate concentration is much greater than Km, then basically you're in a situation where all of your enzyme is bound up in the enzyme substrate complex. And then you have the high energy transition state, and then the enzyme product complex, and then dissociation of enzyme product complex to give you free product and free enzyme. When you're in this situation, when the enzyme substrate complex is more stable than the enzyme and substrate individually, then if you do things that, if you make changes to your enzyme that uniformly stabilize the transition state and the enzyme substrate complex. So if we bring the transition state down by a couple of grid units, and then we do the same thing for the enzyme substrate complex, we actually won't have improved catalysis at all. In blue, I'm going to show you the curve for what we just did in blue dotted lines, and I'm not going to try to say what we did changes the product. Compare the activation energy here, delta G double dagger before we made the change, and then delta G double dagger after we made the change. What do you notice about that situation? Say that again. Go ahead. They should be the same, right? Because the enzyme substrate complex is lower in energy than your starting enzyme and substrate by themselves, if you do things to make the enzyme bind the substrate more, and those things also make a similar change on the transition state, then you've got no improvement in catalysis. So if your enzyme operates under these conditions, where the substrate concentration is already higher than your Km, it makes no sense for the enzyme to try to evolve tighter binding. Tighter binding is not going to get you anywhere. Only at that stage, only speeding up Kcat will get you anywhere. And you can see that by looking at our rate law under those conditions. When substrate concentration is much greater than Km, the only way you improve the speed of the reaction is by enhancing Kcat or by increasing your enzyme concentration. So, and evolutionary ways to do that, maybe you increase the expression level of your enzyme. That's without messing with the enzyme substrate binding, or maybe you optimize the active site to promote catalysis. In contrast, if you're under the situation when in which Km is much greater than your substrate concentration, so again, this will be energy and this will be reaction coordinate. If Km is greater than your enzyme substrate, than your substrate concentration, what that means is that at equilibrium, not a lot of your enzyme is bound by substrate. And then you've got the transition state, the enzyme product complex, dissociation to give enzyme plus product. Here is the transition state. In this case, increasing binding by a uniform amount, increasing the stability of the enzyme substrate complex and the transition state by a uniform amount actually does enhance catalysis. And you can see to a point. So let's see. Sorry, I'm getting a little ahead of myself. And again, if you have a question or a comment that you want to say, feel free to just break in. While I'm looking down at the iPad, it's sort of difficult to see your faces on the screen. All right, so here is the delta G double dagger before the change. Here is the delta G double dagger after the change. And I suppose we could have made the change more dramatic so that we could actually see. I apologize. All right. Suppose we changed the stability of the transition state by exactly the same amount as we changed the stability of the enzyme substrate complex. Now I'm hopeful that you can see that this free energy difference here is smaller than this free energy difference there. And under this situation, if we stabilize both the enzyme substrate complex and the transition state by similar amounts, we will improve catalysis up to a point. Now, why do you think I say up to a point? At what point does it stop being useful? Right, when the enzyme substrate complex becomes as stable or more stable than the starting materials. I'm going to draw that line right here. So once you get to that point and you dip below that level, see, before there, before you get to that point, your starting point is the enzyme substrate complex, and so it doesn't matter. Your starting point is the enzyme and substrate separated. It doesn't matter really what you do to the enzyme substrate complex, because you're just, whatever you do, you're lowering the energy of this barrier relative to your starting point. But once you get below this line, any further efforts to decrease the free energy of the enzyme substrate complex lower the free energy of your starting point, and now whatever you're doing there from that point on is sort of counterproductive. So under this situation, what would nature do to improve catalysis? Well, you could start to try to evolve for better enzyme substrate binding. But once you get to this point, it doesn't do you a whole lot of good to optimize binding further than that. All right? Questions so far? Okay. All right, Kim, let me try again. That's all right. Someday, as all of you move on into regular life and start to have your own family, you may encounter the author Mo Willems, who writes books. There's the Pigeon book. There's the Knuffle Bunny series. All of these are excellent. And then there's the Gerald and Piggy series. And the Gerald and Piggy series is really a racket because there's like 100 different books and kids want them. But there's this sort of bumbling elephant and his best friend Pig. And they have one of the books where Piggy wants to learn how to fly. And Gerald tells her that will never happen. And she tries and she tries. And after every try that fails, she says, "We will try again." So that's an aside for me to use the phrase, "we will try again," with this energy reaction coordinate energy diagram. Enzyme and substrate, transition state, enzyme substrate complex, enzyme product complex, enzyme plus product. Looks like I need to move this one over and that one over a little bit. Okay. So before we do anything, the activation energy for the reaction is the difference in free energy between enzyme and substrate and transition state. Not this difference. The enzymes... Okay. I might have done, and that was my mistake. So until the enzyme substrate complex reaches the stability of your starting materials, it is not the starting point, right? The starting point is your lowest point on the energy diagram on this side. So if we try to decrease the energy of the enzyme substrate complex and the transition state by similar amounts, then there is our new delta G double dagger. Yeah, sorry for the confusion. I think I did do it wrong the first time, so thank you for making me stop and fix that. All right. Other questions? Right, and the reason we're starting with the ES is because it's lower in energy than over here. Does that make sense? Yeah. And so the big point to take from this is beyond a certain point, it doesn't make sense for the enzyme to improve its binding to a substrate because that's not going to improve catalysis. And so what you see in enzymes, this is really kind of cool, a lot of enzymes have Km values that are equal to or maybe just a little bit greater than the physiological substrate concentration. They're sort of tuning themselves for the environment that they exist in. So without spending too much more time, I always spend too much time on stuff. But this is kind of cool, and it's something I haven't understood before. If you want to think about what it means to be perfect, Jesus said, "Be ye therefore perfect." And we, in the church, continue to talk about exactly what that means. And Elder Holland, I think, gave a lovely talk not too long ago about "Be ye therefore perfect" eventually. But for enzymes, perfection is very well defined. An enzyme can be no faster than the diffusion limit of water. What is the diffusion limit? Well, the fastest something can diffuse in water we'll call bimolecular diffusion. That is, how fast can two different molecules find each other in water just by bumping around into each other. The fastest that can be is 10 to the 8 to 10 to the 9 per molar per second. That's the rate constant for bimolecular diffusion. And if you look at those units, they're exactly the same units as Kcat over Km, that so-called specificity constant, also in units of per molar per second. So it turns out that if your enzyme has Kcat over Km equals 10 to the 8 to 10 to the 9, it is perfect. It is as fast as diffusion. It works so fast that the rate determining step is no longer the enzyme, but rather diffusion in water. And that's as fast as you can get. So you might expect, because reaching this diffusion limit involves two different numbers, that there might be multiple ways to have a perfect enzyme. So let me give you an example. The enzyme carbonic anhydrase is one of these so-called perfect enzymes. It has Kcat over Km equal to 8.3 times 10 to the 7 per molar per second. So close enough. Km for this molecule is 0.012 molar. So a 12 millimolar Michaelis constant, and that would put kcat, I haven't done the math specifically, but in the area of 10 to the 5 per second. That's right. That's right. And there would no longer be, and so you don't typically see that. Just to repeat the question, if kcat over km were greater than 10 to the 9, that means that the enzyme is more perfect than it needs to be. And there's no evolutionary pressure for that to happen because, of course, life and evolution takes place in water. And once you reach the diffusion limit, speeding up your enzyme further no longer gets you any acceleration in chemistry because you're just limited by the diffusion rate of water. The contrast between possibilities will become a little bit clearer here when I compare the numbers for carbonic anhydrase with the numbers for triose phosphate isomerase. This is an enzyme in the glycolytic pathway. Sometimes we call this enzyme TIM. And kcat over km for this enzyme is equal to 2.4 times 10 to the 8. Now, the substrate concentration for triose phosphate isomerase, its substrate is dihydroxyacetone phosphate, and its substrate concentration is a lot lower than the substrate concentration for carbonic anhydrase. And so Km for this enzyme is also a lot lower, 2.5 times 10 to the minus 5 molar. And that puts kcat actually needing to be on the order of 10 to the 13 per second. So if your substrate is present in a lot high concentration, you don't need kcat to be as fast as you do if your substrate is present at a really low concentration. So again, enzymes will tune their Km values to be close to the physiological concentration of the substrate, and then at the same time, they need to optimize kcat to get your kcat over Km all the way up to this diffusion limit. So, multiple ways to become a perfect enzyme. Is there a gospel lesson in that? I don't know. There's only one path. But fortunately, Jesus meets us wherever we are. I'm not sure whether he's kcat over, or we're kcat, or he's km. The analogy does not work, and so I'm sorry for even going there. Okay, that concludes Chapter 9. So we spent a ton of time talking about molecular orbital theory, quantum mechanics. We spent a ton of time using what we learned there to talk about structure, reactivity, conformations of organic molecules. We've learned about reaction coordinates. We've learned about thermodynamics and kinetics. Now we're going to start showing you the classic organic reaction mechanisms informed by what you know already about molecular structure and thermodynamics and kinetics. What we're going to talk about will be definitely a review of some mechanisms that you've learned in your undergraduate organic chemistry courses. However, the mechanisms will be more nuanced than perhaps you expect. Much of what we talked about in undergrad OChem were limiting cases, and you're going to see that the lines blur between various mechanistic possibilities depending on the different structures of the molecules that we use and the conditions that we run the reactions. Your goal here is to have a general feel for how organic reaction mechanisms work and how changes that you might make to structure or conditions might impact the mechanism of the reaction. So in Chapter 10, we focus on addition and elimination reactions. And so for addition reactions, we're going to see sort of various options. These typically involve pi bonds. So this will involve alkenes, alkynes, carbonyls, and arenes. There are multiple types of addition reactions. We classify them as electrophilic, where you add an electrophile to, and the abbreviation for addition is AD. You add an electrophile to your alkene, alkyne, or etc. You can also have nucleophilic addition. We tend to see that most with nucleophilic addition to carbonyl compounds. And then there's also radical addition to these kinds of compounds. And we typically abbreviate mechanisms with addition, and then we might say electrophilic, and then we'll include a number to indicate the molecularity of the reaction. So, for example, ADE2 indicates electrophilic addition that is bimolecular. Okay, so we're going to start our discussion with carbonyl hydration. And what we say for carbonyl hydration will also be true for forming hemiacetals. Same reaction, only you're using water versus an alcohol for hemiacetal formation versus hydration. So the classic mechanism that is operative under most circumstances is concerted proton transfer. Proton transfer that's concerted with nucleophilic attack. And we will call this reaction general acid, that it's catalyzed by a general acid, because the rate is determined by this slow step that involves your acid. So I'm going to write out the major players. You've got water, you've got your acid, you've got the carbonyl. Concerted proton transfer means that as the nucleophile is adding to the carbonyl carbon and the pi bond is breaking, we are also protonating the carbonyl oxygen. The way we've drawn these arrows is important, and when you're drawing mechanisms, you need to be thinking about things. So your text points out that you can think of these reactions as nucleophile attacking electrophile or HOMO attacking LUMO. Lone pair electrons in the HOMO on oxygen attack the carbonyl carbon. They attack the pi star. They attack the carbonyl carbon because that's where most of the pi star is. You know that because of orbital polarization that we talked about earlier. You dump electrons into the pi star. You have to break the pi bond so those electrons move out onto the oxygen. And then in a lot of ways in the past, I've just moved this arrow directly to protonate the carbonyl oxygen. But your book is more technically correct. The electrons that are getting the proton are the high energy lone pair electrons on the carbonyl oxygen. So all of this takes place in the same step. You would predict your rate would be first order in carbonyl and first order in acid. After that, you have the following oxonium ion, which is deprotonated in a fast step to give you, and I won't show that with arrows because you can figure that out yourself, to give you the gem diol or the ketone hydrate. So, question so far? Yeah, it's a great question, Isabella. You can't label electrons, and I think you wouldn't know it experimentally. There would be no way to tell. I think though from MO calculations, you could be pretty confident that it's not the pi electrons picking up the proton, but rather the higher energy lone pair electrons. So it's more of a that just makes sense thing and is probably verified by calculations than you can tell that that's the case. I can't think of an experiment off the top of my head that would show that. Good point. And ultimately, Isabella, I think you're right that electron pushing is mostly bookkeeping. The real things that matter are the locations of the nuclei along the reaction potential energy surface, and that's the kind of thing you can observe. So you're right, you wouldn't necessarily be able to tell that. All right. Other questions? Okay, we got 10 minutes left, and I have to turn to the side to look at the clock. So if it gets too late, remember that on my iPad it is eternally 9:41 on Tuesday, January 9th, whatever year that is. So you'll have to let me know if I don't see that we're out of time. So if the acid is involved in the rate determining step, you would predict that changing the acidity of that acid might influence the rate of the reaction. And in fact, if you vary the acid and then plot the log of the rate of the reaction versus the pKa of the acid, you get a linear relationship here, and it's basically a Bronsted plot that was similar to something we discussed, I think, in Chapter 8. Negative slope alpha times pKa plus C. And this number alpha here really represents extent of protonation in the transition state. And you can do a similar study with different nucleophiles, where you plot the log K versus beta times pKa of the conjugate acid relative to your nucleophile. And this beta represents the extent of nucleophilic attack in the transition state. And so you can measure these numbers, and it turns out that the number stays pretty constant even if you make changes to the carbonyl compound. So, for example, 1,3-dichloroacetone has an alpha value of like 0.27 and a beta value of 0.50. That basically means that in the hydration reaction for this carbonyl compound, the oxygen-hydrogen bond is maybe 27% formed, whereas the oxygen-carbon bond is maybe 50% formed. This really sort of tells you where your transition state lies along the potential energy surface. So another example, let's see. And I guess I spoke incorrectly. These alpha numbers don't stay constant from one carbonyl compound to the other. They do vary. But if you change what I meant was if you change the identity of the acid, you can generally plot the rate in this linear free energy relationship and get a slope that is a constant. So for this particular 3-chlorobenzaldehyde, the rate, the extent of protonation versus nucleophilic attack in the transition state is about equal. So we can think about how changing the acid might affect the transition state of this hydration reaction with one of these horrible square more O'Farrell-Jenks plots, which you might hate, and if you do, that's fine. The line there represents the reaction pathway for the fully concerted reaction. On the x-axis, we're going to have beta, which is extent of nucleophilic attack. And on the y-axis, we're going to have alpha, which is extent of protonation. Can I do that? Is that okay? And then energy will be on this imaginary, well, on this z-axis coming out of the page. On the upper right-hand corner, we will have starting materials. Upper left-hand corner, rather, we have starting materials. Lower right-hand corner, we have products. So this would be our ketone, our acid, and water. If we don't move along the x-axis, but instead move along the y-axis, we would have complete proton transfer prior to nucleophilic attack. So you'd have your protonated oxonium ion and water. In contrast, on the upper right-hand corner, you would have complete nucleophilic attack prior to protonation. And then, of course, your product here would be the hydrate and your conjugate base of your acid. Make sense so far? Questions you want to ask? So I got to say, Isabella, did you have something? Okay, sorry. I saw the yellow box on your name, and so I thought maybe it said something. I got really excited when I saw this because I can remember teaching 352 and struggling to provide students with tools to understand when a nucleophile could attack first and then protonation happens versus when you have to protonate first and then nucleophilic attack happens. And it turns out that the reason it's hard to tell people when that happens is because reality is you might have a pathway along a continuum between any of these extremes. And so that's the broader insight you're getting from physical organic chemistry, that mechanisms often adopt some intermediate pathway that's along a continuum between two extreme possibilities. So let's just say that we're talking about, for our ketone, we're talking about 3-chlorobenzaldehyde. So we would locate our transition state somewhere where alpha equals 4.46 and beta equals 0.44. And these axes go from 0 to 1 in the x direction and 0 to 1 in the y direction. So 0.4 would be something like here. Okay? So now let's talk about how increasing the strength of the acid would affect this transition state. Okay, if we increase the strength of the acid, what does it do to our potential energy surface? What corners of the potential energy surface change? Right, so you're going to lower the energy of anything with A minus. Alternatively, you could say you're increasing the energy of anything with HA. And those, we're talking about relative energies here, and so either of those is acceptable. So it may be easier to see what we're talking about if we think about increasing acidity using a stronger acid as taking the upper edge of this sheet and moving it up in energy. Okay, so now we got to use our intuition gained from kinetics. What, along the diagonal, what does raising this starting material corner do to the transition state? Mario, I saw your finger pointing up and to the left. What is that right? So increasing this corner should move this transition state closer to starting materials, right? And that is simply a statement of the Hammond Postulate. If the starting materials get less stable, the transition state starts to resemble those starting materials. What's the effect of raising this corner? Okay, Kim, you're pointing, but I can't tell which direction we're pointing. So can you? Right. If we increase the free energy of this corner, you're going to tend to roll the marble or the transition state away in that direction. And then you take the vector math, you take the vector sum of those two changes, and your new transition state is here. And actually, I got to use a different color because I don't like that dot, and we have less than a minute left. Your new transition state is here. Let's look at what that change did with respect to nucleophilic attack versus protonation. By increasing the acidity, we don't change the extent of protonation in the transition state, but we do change the extent of nucleophilic attack. If you use a stronger acid, the nucleophile doesn't need to attack as much before the acid protonates the carbonyl oxygen. And this makes sense, right? As the nucleophile attacks, you expect a buildup of partial negative charge on the carbonyl oxygen. If your acid is strong, you shouldn't need as much partial negative charge in order to protonate. Okay? So, so though it may seem counterintuitive that by making our acid stronger, we don't change the extent of protonation in the transition state, but you come to that result by a careful consideration of this kind of reaction coordinate energy diagram. All right, so that will end our official lecture. If you need to leave, feel free to do that. If you have questions, I'm willing to hang around for a little bit, and I'll record whatever we do so that anybody that has to leave can come back and see. But otherwise, if you don't have questions, don't feel bad about logging off. And I will see you next time on Wednesday when we will continue with Chapter 10.